before Bitcoin in 2009, they had what were called classical consensus protocols. And all it really is you have a bunch of computers that are distributed and connected via the internet or whatever, and you want to have a database where the database is replicated across these computers, and you want to keep everything the exact same in terms of the database. So let's say Amazon servers. They don't want a situation where somebody is accessing one of their servers to buy an item, and somebody halfway across the world buys that item at the exact same time. They want to make sure that everything is synced up, so all of the servers agree on what the state of everything is. And all those systems use some variation of a classical consensus protocol. So that's studies or investigations into that have been around for decades.
And the idea is to provide security for the transactions?
Or to prevent duplicate transactions.
Yeah, it's just to keep all of the databases in agreement.
So synchrony.
So that yes, exactly, synchronizing everything.
And so that's a solution to what problem? Like, where do we see on Earth right now, where are these problems with asynchrony?
Well, if you had any kind of a system where, let's say, you're tracking your inventory, if there's a change to that inventory, you want that to be registered everywhere that is using that inventory to track. So if those get out of alignment, if they're in disagreement, then one of them's wrong. So it's all about just keeping everything in line with what the actual state of something is.
But this isn't blockchain. This is old news.
No, this is just consensus.
And this kind of came about with the internet in general, right? So, or distributed. Yes. Did it start before Amazon with somebody who has, say, distributed warehouses and is selling across the world? Or is Amazon really the people who pioneered this?
Well, I'm just using Amazon as an example, but I mean, it's been around for a long time. Okay. I don't know what the first industry was to use these, or how widespread it is, but any kind of system, Facebook, those are just examples. Any system where you have servers that are distributed, where they need to agree on the state of something, is going to be using some kind of consensus protocol.
Okay.
And so all blockchain is trying to figure out a way to apply this to money, because before Bitcoin, there was a lot of work done on trying to figure out how would you do digital cash. And the problem always was that you need a central warehouse that has serial numbers on all of these digital notes, because if you don't track every single transaction with a central clearinghouse, there's nothing, if it's electronic, there's nothing to prevent me from just copy pasting it and spending it 20 trillion times. And, obviously the system wouldn't be able to work very well. Every time that you spend it, you have to notify the central clearinghouse and say, hey, look, I'm signing this, I'm passing it to this person, make sure you mark that down in your ledger. That way I can't turn around and go spend it with somebody else, that same note.
Got it.
And so there was a lot of work done in the 90s trying to figure out some way to solve this double spending problem without having a central clearinghouse. And
the way that the central clearinghouse solves this problem is because they issue a set of notes that have set serial numbers on them. And so if you spend a note, that person can check with the central clearinghouse to make sure that it's the same number.
Yeah.
Like those numbers aren't duplicated.
Exactly. So if I were to send you digital currency of this kind, those numbers that are associated with those notes, I would actually have to communicate with the central clearinghouse and say, hey, I am sending these serial numbers to this account over here. Make sure you mark that down in your system. So they would have to track who has everything.
Got it.
And then what blockchain does is it figures out a way to solve the double spending problem without having a central clearinghouse. So it's sort of like a database that has no system administrator. You think of a sysadmin normally has permissions to be able to edit whatever they want in a database. But with blockchain, there is no system administrator that can edit everything. The read and write permissions, or the write permissions, I should say, are distributed among people who have cryptographic keys. So I guess I would need to sort of explain public key cryptography and what hash functions are.
Okay, let's get there in a second. But so is that ledger then available? Like, does everyone download that entire ledger every time they do a transaction?
Only if you want to run what's called a full node. A full node is where you do actually download the entire history of all transactions from the initial state all the way to the current state of all the accounts. And you actually replay all of the transactions to validate that it is cryptographically correct.
But that's not necessary for every transaction.
Well, it is. Well, okay. So what people actually normally do is you connect to a full node who will broadcast your transaction to the network for you.
So you basically pay somebody to do that.
Well, a lot of services just do it for free. The payment is contained in the transaction. That goes to the miners who are processing the transactions.
And the terminology here, transaction is when a new coin is added?
So a transaction would be, okay, I think I might need to explain public key cryptography for it to make sense.
Let's do it.
Okay.
Okay, so in symmetric key cryptography, if I want to send you a secret message, we have to exchange keys first, because the key can be used to encrypt the message and decrypt the message. And once I've encrypted it, it's unreadable. If you don't have the key, it's impossible for you to read it. It's complete gibberish, random symbols.
And this message could be payments, or it could be anything?
Yeah, in general, it could be anything. Any data can be encrypted.
Gotcha.
There was a advance, I don't know if this was in the 60s or 70s, an advance where they discovered public key cryptography, which is not symmetric encryption, but it's asymmetric encryption. So how that works is I have two keys, actually. I have a private key, and that private key mathematically corresponds with a public key. So the way that works is anything that I encrypt with my private key can only be decrypted with my public key, and anything that I encrypt with my public key can only be decrypted with my private key. And that's nice because that means we can create a secure communication channel without having to exchange a private key first, because the exchange of a private key over an unsecure channel could have somebody could intercept that and then decrypt the rest of our communications. So if you also have a private key and a public key, I can take your public key, encrypt my message, send that through the internet, and it doesn't matter who intercepts it because only you can decrypt it with your private key.
Interesting. So it's kind of like your name is your public key and your signature is like your private key or something like that?
So it's alphanumeric, 64 characters of hexadecimal. It's 256 bits of data, but it's just basically random. It's completely random looking data, but your private key is cryptographically linked to your public key.
Okay.
And this is basically, it's an account. It's the equivalent of a Bitcoin bank account, basically.
Got it.
And so you mentioned signature. This is nice. Whoa, I don't know what that was.
That sounded violent.
Yeah, that's weird. I felt that.
Forest monsters?
I don't know what that was. Yeah, there's like car alarms going off, I think. Anyway, but you can use public key cryptography to sign a transaction. So instead of encrypting something with my public key, if I say I want to do a transaction on blockchain, I take the unencrypted data of the transaction. I want to send 5 Bitcoin to Bob, whatever that looks like in the format of a transaction. take that, if I encrypt it with my private key, once that's sent out publicly, you can verify that I signed it or that I encrypted it, because it can only be decrypted with the public key, which everyone has access to. So the system can verify, they know that whoever owns this private key encrypted it with that private key, because it can be decrypted with the public key. So it's a way of signing, it's a way of authenticating transactions.
So this isn't actually a way of encoding transactions so that they can't be read. This is a way of signing things so they can be verified.
Exactly.
I got it.
Exactly. It's a method of authentication. So yeah, and that's what gives you the right permissions to your account, essentially. You are the one who only has right permissions to that account, and you can use it to broadcast transactions, and then the miners are responsible for processing those transactions.
Cool. So let's talk some applications of this technology.
Have we finished with the whole process of actually like how the front end of it works? Because you said that in order to explain the difference between transaction and mining and adding something, you had to explain encryption first.
Yeah, so I mean, there is the other piece of it is hash functions, which a hash function is, you can take a variable length piece of data, so it could be something as small as 1 bit, 1 0 or a 1, or as large as you want it to be, a library worth of data. Run it through a hash function, and it will spit out a fixed length, pseudo-random looking piece of data that's 256 bits, or depending on the hash function you use. And the feature of a hash function is that, I guess, two main things. One, if I change one little bit of data, let's say this video that we're recording, once we're done recording that, I can run that through a hash function and it'll spit out a certain string, the same string every single time. I can change 1 pixel in that video and run it through the same hash function, and it will spit out a radically different output. So it's a way of maintaining the integrity of data. A lot of times if you download something, they say, hey, here's the hash of it, download that and run that. It's a way of making sure that if it matches the hash that you see, you know that the file was not tampered with. Even 1 bit is changed, and you'll know about it because it'll produce a completely different hash.
Oh, that's awesome. So this could be amazing for like elections or for fake news or things where you're worried about the authenticity.
Mm-hmm.
Sure. And the way that they use hash functions is it's also what's called a trapdoor function. So let's say I take 2 really huge prime numbers, and I don't tell you what they are, and I multiply them, and then I give you the result, and I say, okay, tell me what the 2 numbers were. You would be kind of hard for you to work backwards and try to figure out what the 2 inputs were just with the result of the output. And the naive way of doing that would be to just randomly brute force it, guess and check, multiply numbers together until eventually you stumble upon whatever 2 numbers it is. But the nice thing about that is once you find those 2 numbers, it can be verified in a heartbeat, right? You just got to multiply 2 numbers together. So that's kind of a hash function. If I just give you the result of a hash function, which is that fixed length 256-bit pseudo-random string, it's basically impossible for you to work backwards to figure out what the input was. But if I give you the input, you can verify that that's the correct input in milliseconds. So what they do for Bitcoin and blockchain, when they talk about the cryptographic puzzle that they're solving, what they're actually doing is taking all of the transactions that have recently been broadcast to the network, combining them all into a block. They include a few other things in there, like the hash of the previous block and a number called a nonce that they increment. And they sit there and they hash it and they check. So the way the protocol works is you have to find a hash that begins with a certain number of zeros. And because the output's going to be basically more or less random, when they hash it, if it doesn't start with a certain number of zeros, they'll increment that nonce by 1 or however they want to do it, hash again, look at the result. Does it begin with a certain number of zeros? Yes or no? And they do that. And that's why they do, gazillions and gazillions of hashes per second. They're racing to try to find a solution to where whatever that nonce is, combined with all the transaction data, outputs a hash that satisfies this criteria of beginning with a certain number of zeros. And whoever finds one that satisfies that then is basically elected the leader for that block. They can determine the order of transactions. They determine what transactions get included and what transactions aren't included. So I mentioned earlier the sysadmin. The fact that there's no sysadmin on a blockchain, what they're doing is racing each other with these hashes to try to find the solution first, to then have permission just for that block to be able to make the decision, okay, we're including these transactions and they're going to be in this order. And then once they publish that solution, now everybody takes the hash of that block, includes it in the next one, gathers more transactions, and the process continues on and on. So it's gamified through hash power as a way of securely randomizing who gets to be the next entity to determine the order of transactions. That prevents any one entity from controlling everything overall, because then they could do things like censor transactions and have undue influence and control over the network. So it decentralizes power and control over the network. And also it's a way of solving the double spending problem. Instead of having a central clearinghouse, you now have this way of being able to make sure that transactions cannot be double spent.